Hello everybody, so this is the third video of chapter 6 for the reinforcement learning course. So in the previous video we discussed prediction methods for temporal difference, the temporal difference approach, and now we're gonna discuss control. Okay, so the prediction problem is where we fix a policy pi and we want to determine the value of the state value function. Whereas here in control, we'll want to find the action value function and sequentially refine our policy. But before we pursue with that, I just want to come back about some comments I made in the previous video. I realized that when I mentioned batch learning, my comments were a bit confusing, so I'd like to correct these. Okay, so if you go back to slide 21, I've changed a bit the wording. So in the previous video, I might have mentioned that when you do some batch learning, you perform the updates at the end of each episode, whereas this is not entirely true. It's instead at the end of the batch of episodes. So you feed multiple episodes to the algorithm, then the algorithm stores the various updates that need to be done instead of applying them right away. And then once you went through all of the episodes, only then at this point you update the value function and the policy based on all updates recommended by the your updating algorithm. Okay, so in batch learning, you pass a batch of episodes, which is a set of episodes, and then you make the updates only at the end of the batch. Okay, so I wanted to correct what I said in the previous video. This is now the correct explanation. I've changed a bit of the wording in that slide if you compare to what was there in the previous video. Okay, so let's pursue. We were at slide 28. Okay, so as mentioned, we're now gonna tackle the control problem, where we not only want we don't only want to have an estimate of the state value function, but rather now we want to optimize the policy and find, of course, the associated optimal value function. So as we've done in previous chapters, we're going to follow a pattern analogous to the generalized policy iteration, where we do some policy evaluation steps to refine our estimate of the value function and make it closer to the true value function of the current policy estimate. And then we're going to alternate these policy iteration steps with policy improvement steps, where based on the current estimate of the value function, we make our current policy greedy with respect to that value function to try to improve the policy and eventually converge to the optimal one. But the difference with what we've done in chapter 5 is that now we're going to use temporal difference methods for such purposes instead of the Monte Carlo approach of chapter 5. And again, we're going to see that all the approaches presented in this chapter, they fall into two main classes, which are on policy algorithms and off policy. Okay, so I won't repeat the distinction between both right now because we've already mentioned that, but I'll refer to it subsequently. Okay, so the first approach we present is an algorithm called SARSA. Okay, so SARSA is an on policy method for control. Okay, so what's on policy again? It's that the same policy that we're estimating and which we want to improve so as to converge to optimality, then the same policy that is currently refined is used to generate the episodes. Okay, so this is different than off policy, where you had two policies, one that being the behavior policy, which generates the episodes, and the second one being the target policy, which is your estimate of the optimal policy. And on policy, the behavior and target policy are the same. Okay, so the same policies used to generate episodes and to estimate the optimal policy. Okay, so that first on policy method we're going to present is called the SARSA algorithm. Okay, so when we do control, again, we don't want simply the state value function v. We rather would like to have the action value q. Okay, so the function q, which gives the value of all actions in a given state. And why do we need this value function instead of v? It's because when we do policy improvement, we must compare the value of the various actions A for a given state S so as to improve on our policy. Okay, so we for controlled problems, we want the Q function or the action value function instead of the state value function v pi. Okay, so TD0 we saw last time, it's a prediction method which gives you v pi rather than q. Okay, so as we mentioned before, an on-policy framework requires continuous exploration. Okay, so in your episodes, if you want to estimate the value of all actions in all states, you must repeatedly sample them in order to have eventually sampled them an infinite number of times if you want to converge to the true estimate. Okay, so if you want convergence of your estimates to the true value of action values, then all state action pairs should be visited an infinite number of times. So you have to have a policy which continuously explores. So for that reason, you cannot use a fully greedy policy. You can only, for instance, use an epsilon soft or an epsilon greedy policy which continuously explores. So as we mentioned earlier, your algorithm will not converge to the best policy overall, but rather it will converge to the best epsilon greedy policy. Okay, so how does this SARSA algorithm works? Well, so first, why SARSA? We're gonna see the justification for this name. So SARSA means the S is for state, A is for action, R is for reward, S is for state, and A is for action. Okay, so once we're gonna see the algorithm, this name will make a lot of sense. Okay, so the algorithm works as follows to generate the various episodes and to refine the estimates of the Q function, which is the action value function. Okay, so assuming that in an episode, your system is in state ST at time t, you've taken an action AT in that state, and then you observe. So, okay, assume at the beginning you're in state T and take action AT. So then what's going to happen at the next step, you observe a reward RT plus 1 and transition into the next state ST plus 1. And then you must decide what action you will take at time T plus 1. Okay, so for the given previous pair of state in action and the previous reward, let's say you transition into a new state, you must decide what action you take in that new state. So the step number 3 here explains how you choose your new action. So the action AT plus 1 is selected according to the current estimate of the optimal policy pi. Okay, so for example, if your policy pi is an epsilon greedy policy, so if you attempt converging to the best epsilon greedy policy, then you would do the following. Okay, so that you would first calculate in your current state ST plus 1 what would be your optimal action according to your estimate. So your optimal action or estimated optimal action would be the action which would maximize the current estimate of the action value function evaluated at the state st plus 1 and action A. So the action A which maximizes this guy here is your optimal action state st plus 1, uh, your estimated optimal action. So now what you will do here to select your next action, you will select either the greedy action with probability 1 minus epsilon or any randomly selected action with probability epsilon. Okay, so basically to select your next action, you look at your greedy action into the uh, the current state at time t plus 1, and you can follow an epsilon greedy approach where you pick the greedy action with probability 1 minus epsilon, or you randomly sample with probability epsilon. So, and then if you do that, you observe the following sequence of states in action. So you have state st at the previous step, action at, then this is a mistake. It should be rt plus 1 instead of rt. Apologize for this. Then state st plus 1 and action at plus 1. Okay, so this reads as SARSA, which justifies the name of the algorithm. Okay, so let's say you're here at time at plus 1. So then if you want to continue generating the episode, it's exactly the same again. So you will observe a new reward. You will transition randomly into some new state, and then you'll have to select your action at time t plus 2. So you can use the same previous rule that we just showed to select at plus 2 and continue like this until you reach the end of the episode. Okay, so this explains how to generate the episode with your SARSA algorithm. But when you go through an episode, you not only have to generate the episode, but you have to update constantly your estimate of the action value function. Okay, you want to, while you go through, you don't want simply to generate the episode, you want to learn from it. So refine your estimate of the value function. So how would this work? Well, at every time step, what's going to happen is the following. So provided that your time t state is not the terminal one, because of course if you're in the terminal state at time t, you know the value of that state is 0, so you can stop there and there's nothing to do. Okay, but if you're not at time t at the terminal state, then we'll start with the second equation here. The second equation says that for all state action pairs which were not visited at time t, you keep the same current estimate for your action value function. So your estimate at time t plus 1 is simply your estimate at time t. But for the state action pair you've visited at time t, then your next estimate is your previous estimate plus, again, the learning rate times the target minus the current estimate. So here we see again the same type of formulas we've outlined in the previous chapter, in chapter 5, which is a particular case of the update rule. Next estimate is previous estimate plus learning rate times target minus current estimate, where that part here, the target minus the current estimate, was called the error. So well, I said in chapter 5, but I think it's even in the beginning of the chapter 6 we discussed that. So here, why the target takes this form? Well, it's because if qt, our current estimate of the value function, was a perfect estimate, so if this was the true value function, then the expectation of this guy would be the exact action value function q star STAT. Okay, so if this estimate was perfect, then this guy would have been exactly, let's write it, would have been, so let's say an expectation, the expectation of this guy here, if this estimate of Q was perfect, would be equal to Q star ST. Okay, so when we say expectation, it means conditional on state T and action T. Okay, so here, this is why we see that provided this estimate of Q is perfect, then this would be an unbiased estimate of the true value of the, sorry, this is, how can I say that? Okay, so here I use Q star. It's not entirely true because if we use the optimal epsilon greedy policy, it's not the true best policy, but it's the optimal epsilon greedy policy. Okay, so sorry for this abuse of notation. So here Q star is not the fully optimal one, but it's the best optimal, best epsilon greedy policy. Okay, so this rule has the same form than what we did earlier. So we're not in unknown territory here. Okay. Okay, so it means throughout the SARSA algorithm, on every time step, we generate a new state action pair based on the previous rule to select the action, and based on the new state action pair generated on each step, we can update the estimate of the action value function of the state action pair from the previous step, from the time step t here. Okay, and here, so we said that the algorithm should be analogous to policy evaluation and policy improvement. So if we go back here, then clearly this is similar to a policy evaluation step because we're refining our estimate of the action value function. But where is the policy improvement step here? So it's the third step here, which is analogous to policy improvement, because by selecting the action, which is the greedy one, according to our action value function estimate. Okay, so it's the greedy, selecting the greedy action with 1 minus probability epsilon. It pushes the policy towards the optimal one because recall the policy improvement is exactly that. The policy improvement entails finding the new policy which selects greedy action with respect to the current estimate of the state value function, and this is exactly what happens here. Okay, so this step here, the third step, is the one which acts like the policy improvement step. Okay, so this algorithm now it's intuitive, but does it make sense? Do we converge to the true value function? Is it theoretically founded? And the answer is yes. Okay, so there exists some convergence results in the literature. So it can be shown, for example, so if each state action pair is sampled an infinite number of times, and if the policy that we use converges to a fully greedy one. So for example, if we have an epsilon greedy policy, well, in theory, we could shrink epsilon through time so as to slowly converge to a greedy policy. And if we have these type of conditions, then it can be shown that the SARSA method will converge to the optimal policy with probability 1. Okay, so this is a very nice result. It says that if you sample episodes for uh, an amount of time which is long enough, then you will become arbitrarily close to the true value of the value function, and you should eventually converge to the optimal policy. Okay, so here just the second condition, we said that you should become arbitrarily close to a fully greedy policy. Well, if you want to do that in practice, we said we could shrink epsilon. So a way to do that is to select your epsilon being 1 over I, where I is the number of the episode you've simulated. Okay, so every time you shrink epsilon on each episode, and this epsilon here, if you select this rule as I tends to infinity, as the number of episodes tends to infinity, epsilon will converge to 0. Okay, so this was the on-policy approach for the temporal difference method, which was the SARSA algorithm. Now we're going to consider another case, which is off-policy Qlearning, and off-policy control with temporal differences. So the algorithm now for off-policy learning with temporal difference, it's called Qlearning. It's from a paper of Watkins from 1989. And here the steps are somewhat similar to what we proposed earlier, but now we use a different rule in Qlearning in comparison to the SARSA. Okay, so for SARSA, what you used is the current estimate of the greedy policy, okay, to select your action. Okay, so you estimated on each step the greedy action, and then with probability 1 minus epsilon, you selected this action, or with probability epsilon, you selected randomly. Here, we won't do that. Okay, so instead, what changes in the update rule is the target here. Okay, so the target is still the reward plus the discount factor, but here, instead of trying to select the next action to update our action value function and to determine our target, we will do a maximization across all next actions. Okay, so here we see that this update rule does not involve AT plus 1. Okay, so it means that whatever action AT plus 1 you will select in your episode, your updates will not depend on it. Okay, so this means that your updates won't depend on your behavior policy. Okay, so this means that when you apply Qlearning, you can use any behavior policy to generate your episodes. Okay, so generate your episodes according to any policy, but then on each time step, you refine your estimates of the Q function or the action value function through this, where in the target here, you take the greedy action to plug in your action value function estimate. Okay. So here, contrarily to SARSA, where you considered a transition from a state action pair to another state action pair, here in the Qlearning, you consider a transition from a state action pair to the next state, and then in the next state, you consider the greedy action, not the action realized in your episode to make the update. Okay, so this is why it's an off-policy method. It's because your policy to select the next action. Here it can be anything. It's not your current, not necessarily your current estimate of the optimal policy. Okay, so let's go back here. So what justifies taking the maximum across all actions? It's because if Qt was the optimal value function, then the maximum across all actions of Qt, sorry for that, Qt st plus 1a, this would be equal. So if you take the action which has the highest value, this would be equal to v prime v star st plus 1, the optimal value function. Okay, so if you replace this quantity here by your value function in the next step, then the expectation of this guy would become exactly equal to Q star ST AT. Okay, so if you had a perfect estimate of Qt, then the expectation of this would be the optimal value function. So this would be an unbiased estimate of the true value function, and this update rule, it would push your current estimate of the action value function towards the true value function. Okay, so this is the justification for why we select the action maximizing this quantity. Okay. So here, as we mentioned, the policy that we consider to generate episodes, it appears nowhere in the update rule because the update rule does not consider AT plus 1 through the update. It doesn't consider what's your policy to generate the next action. Okay. So this means that in theory, any policy can be used in Qlearning to generate your episodes as long as it satisfies the coverage assumption, which is that all state action pairs are sampled eventually with a probability. Well, they're all sampled with probability greater than 0, so eventually they will appear an infinite number of times within your episodes if the number of episodes converges to infinity. Okay. So in that case, Qt, instead of approximating the current policy value function, it directly estimates the optimal value function Q. Okay, so whatever your behavior policy is you choose, your estimate Qt will converge to the optimal value function, which is the value function, action value function of the optimal policy. So here you can converge not only to the best epsilon greedy policy, you will converge to the best overall policy in that case. Okay, so the only condition for this, as we mentioned, is the coverage assumption, which is that all state action pairs are sampled an infinite number of times by the behavior policy. Okay, so we will stop the video here, and we will pursue in the next video with modifications of the SARSA algorithm and other TD control algorithms to improve their performance. So have a nice day.